The observation diary as a source of authentic data. In this talk, I will describe an observation diary activity that provides an easily accessible source of authentic data. My name is Abel, and together with my collaborators Ryan, Justin, Yuhua, and Bitao, we are from the Physics Department of the National University of Singapore. As astronomy educators, we often say that astronomy is for everyone, and the easiest way to get started is to just look up. But what can we expect? There's a wide variety of astronomical phenomena and objects out there, and even more in the vast public archives that are available to anyone with an internet connection. So where do we even begin? On top of that, the heliocentric perspective that textbooks often describe can be confusing and often require three-dimensional visualization. So, how do we bridge this gap? So we start simple. The idea is to go back to basics and follow the example of ancient sky watchers. These are the people who had to figure out the sky from scratch, often as a means of survival. They had absolutely no preconceived ideas about what the sky was to be like, except that the sky that they saw at important times of the year always looked similar. So, from the points of light in the sky, people made patterns and told stories to remember them. And more importantly, ancient sky watchers described the movements in the sky as they saw it and tried to interpret what they actually see. So to replicate this experience, we use simple technology. Just pen and paper to record our observations, and a compass and a watch to establish our bearings in space and time. What we're going to do here is that we want to look out for movements in the sky in a way that ancient sky watchers often did. This results in the observation diary activity. In this observation diary activity, students are tasked to go out and look at the sky for a period of 2 weeks. And they are as far as possible to observe at a consistent time and location and face the same direction each time they observe. But more importantly, they are not required to know any star names or constellations, and they are not allowed to look things up after their observations. Technology use is also kept to a minimum, and students were told to use pen and paper for recording data, and they were not allowed to use photographs for this activity. All in, these restrictions ensure that the data they collect is truly their own. But during each observation, students would take note of the stars, and they would note down the patterns of the brightest points of light. They may decide to make up names for them, and at regular intervals, they would make sketches of the sky with a foreground object or the horizon as a reference point. So the image on the right here shows some student sketches where we see students have identified patterns, and they have tracked the patterns over a period of 2 weeks. We can also see that the moon was visible in one of the observations, but not the other one, and likewise for the other student as well. They would also keep a log and take note of the weather, and all this would go into the observations. Then, at the end of the activity, we need to make sense of the data. Each student will have an individual interpretation of the sky and how the stars moved. And this is from their own point of view, which can be subjective. So, to relate this subjective reality to a common reality that everyone can agree with, students will then discuss their observations with their peers. In small groups, they'll take out their observations and they'll compare them. And depending on where they were facing, their observations and conclusions can be very different. They are free to choose their own observing site and direction, and one student may say, I saw the stars moving upwards. Another student may say, I saw the stars moving to the right. And they often agree or disagree about the presence or absence of the moon. So, you have to recognize that looking from a different direction changes what you see. One student may be facing east while observing, while another student may be facing south while observing. And the difference in observing direction will lead to very different conclusions, even though it is the very same sky that we are all under. In this exercise, students will also see that a change of reference frame, just changing the direction, can make a very big difference in what we see. But in this activity, what students see is the perspective from Earth. However, many textbooks describe the view from space instead. Now, a lot of astronomy textbooks often describe the heliocentric perspective. But for many people, our lived experience is the geocentric perspective. So while we often take it for granted that the moon goes around the Earth and the Earth goes around the sun, this is not entirely obvious from simple observations. And to make things more difficult, diagrams are also confusing because the movements in the sky and solar system, they're not so easily described in a drawing. And instead, you need to have a full three-dimensional visualization to fully understand what is going on. So an example here is the idea of solstices and equinoxes. While we can state the Earth's axis tilt on a figure printed on a page, it's not immediately obvious that this figure represents the view from the Earth with respect to the ecliptic from a very specific direction. And to fully understand this, you need an actual three-dimensional visualization. So to get around this problem, we use a physical model in class. And this is a simple set of pieces on a board. So we have a sun piece that is normally in the center of the board. And we have a planet piece that can be placed on the board to see the position of a planet. We also have an Earth piece that is similar to the planet piece, and the Earth piece is tilted 23.5 degrees, and we can rotate the Earth piece to show diurnal rotation. We also have a moon piece that is placed over the Earth piece like this, and we can move this around to show lunar phases. Then the solar calendar base that we have in the left image here represents a tropical calendar, where the Earth's axis tilt moving around the year can show the effect of the seasons. In the right panel here, we have the zodiac base, which represents the solar system, including its background stars, various vernal points that can demonstrate axial precession, which is relevant when discussing ancient sky watches. And these physical models help students visualize the view from outer space. But more importantly, by turning this Earth piece and moving it along its orbit, students will see that the Earth rotates on its axis and orbits the sun, and this movement carries an observer along so that we see a slightly different sky each night. So, the observation diary paired with the solar system models together demonstrate a complete description of the sky and the solar system. And what we find is that after discussing in their groups, students could mostly agree on how the sky moves by understanding that different conclusions come from having a different observing direction or different observing time. Then, by conducting their own observations, students could also agree that the geocentric universe makes sense to a naive observer with no technology. You would go out to the field, would sit down, I am not moving, but the stars are moving, hence the geocentric model. Then, we reconcile the geocentric universe with the heliocentric universe by explaining this through relative motion. The idea that we have to take a change of reference frame. I am not moving, but the Earth is carrying me along as it moves. So to conclude, the observation diary is an effective, low-cost, low barrier to entry source of authentic data that almost everyone can access. Astronomy is for everyone.